All right, folks, let's get started. Okay. Okay, so everybody, welcome to lecture 33. We're talking about virtual memory. This is an entirely new topic. This isn't a continuation of instructional level parallelism. This is explaining how the world works. It's really cool. This is where I lift up the hood and show you, wow, that's what lives inside all along. To put this in context, here is the next 3 weeks of 61C. This will take us on home. 3 weeks of virtual memory. Then we're going to do some I.O. for basically a week. And then some cool Amdahl's law and economics of cloud storage and the like. And close it up with, HKN surveys and that. So basically it's a full week of virtual memory. Just give me your full attention for this new topic and we'll jump in and have a good time. I was going to show this Colbert report, but there's no Wi-Fi today. But maybe it'll load in by the break and we'll show you the Colbert report. We've got some, I don't know if you know this, but Berkeley's got some national coverage thanks to some overly aggressive policemen. You've probably seen this online, and it made national coverage, so we'll show you about that. So anyway, technology in the news. Technology in the news. This is a company, OCZ, that's always on the high end of the flash storage space, and they have announced that they didn't announce ready to sell, but they announced kind of a research prototype of an 8 terabyte solid-state drive. And the biggest physical device that you can get that's a hard disk drive, is only 4 terabytes. So in fact, they have now, they haven't, when it's a shipping product, I'll believe it, but I'm excited to see that they are potentially in the space to have, even though you're going to pay through the nose, it's going to be astronomical. You're going to pay through the nose for this. But for those who need it, that's going to be pretty exciting to have solid-state drives have actually caught up to hard disk drives. Not the price, but at least the storage. So, in review, this is copied from Wednesday's concluding slide. Pipelining, we saw last time, was a really important thing for being able to squeeze more power, more performance out of our system by issuing multiple requests at once and have this pipeline. That's how you do your laundry in general. That's the first slide he showed is, here's how you do your laundry anyway. No one does the entire load for whites and then waits till the dryer is done and the folder is done and the put-awayer person is done before they start the next one. You start the next one the moment the washer is done. We do that as well. There are some details with hazards that really slow down our optimal case. We do forwarding to route. Remember that we did forwarding for the check of equality in the branch. We have a delayed branch. We've just redefined with a branch how to interpret MIPS. There's interpreting MIPS with non-delayed branch and interpreting MIPS with delayed branch. And the delayed branch means I'm going to do the instruction right after the branch, whether I take the branch or not. It's a whole other way to interpret the semantics of MIPS, and that's what delayed branch is. We also have a load delay slot we have to fill as well. Otherwise, the system will interlock. And interlock means the system's smart enough to just stop and say, there's going to be a load hazard. I'm going to put a bubble right there, and it stalls then. It's called interlock. We saw there are ways to even go past the normal default pipelining with these 4 ideas, and it's pretty cool. And most of these are used in real systems. So these are real things, not just research ideas. These are real active things. And they make 152 more interesting. If you take the next follow-up course from this, which is 152, processor design, you're going to say, well, the boring MIPS system is what you do the first half, and then do this stuff for your final project. So these things are real, and we ask you to do those in upper division courses. It's a lot of fun. So take 152 if you like this stuff. So I had this great idea. We're talking about virtual memory. I'll tell you what that word means in a moment. But I had this inspiration of how to teach this. Traditionally, students have struggled with this topic. And we struggled maybe because we don't give enough time for it. We decided to extend the normal lectures from 2 to 3 to give more time to relax and let it sink in, 1. 2, more time for demos, which is going to help a lot, visual representations of it. And 3, I said, there's got to be some new way to approach it. And I said, what if I have you help me build it? So rather than tell you, we've built a car that does this many miles an hour and this is how it works, I'm going to ask you, how would you build a car that did this many miles an hour? And you're going to kind of from bottom up, almost like the Occupy movements, from bottom up. It's really not a top-down. It's a bottom-up movement, a grassroots movement. We will come up and design virtual memory ourselves with a spec. Here's the spec. I want to do a journal. I want to do an electronic journal. So I want to keep my private thoughts and cares and hopes and aspirations on an ebook. But the problem is, it's 1970. So I'm just about the time where Dan's getting born. Mike's about a couple years older than me. We're the same age, Mike? I forget. I think you're like the same age, roughly. Anyway, the point is, none of you are born yet. You're all twinkles in your parents' eyes. And we need to build this ebook. So from, I don't know how you send messages back to the people in 1970, but you somehow do that, and you got to help me with this. Why do I say 70? Well, we want to be able to read and write words on a page, right? That's what a journal is. It's a blank. Has anybody, raise your hand. You bought a blank journal book? Anybody write a blank journal book? Raise your hand. Hi, I'm proud. Look at these people. Good for you. All right, so maybe 10% of you own, and what you do is you go and you buy a blank book, and you just fill it in. But you can fill it in any order. You can start from the front, you can start in the middle, you can insert pictures, all that stuff. You want to be able to have that ability. So you get a blank journal, you want to be able to write anywhere as you do in a normal journal, okay? Here's the problem. It's 1970. This journal only has enough physical memory for 4 pages. So you're kind of limited in how many pages you can ask somebody to write a journal. And there's another problem of how many words are on a page. But that's part of the constraint, okay? It's a small system. It's 1970. Bear with me for that one, okay? So 4 pages. So each page is actually 32 bytes. So it's not a lot of journaling, but you're getting started, right? We're getting the ball rolling on this e-journal model, okay? 32 bytes knows that 5 bits is all you need to specify which particular character. You know, the 1 byte stores a character, right? So 5 bits to specify in there. This is called the page offset. Right, you can imagine that, right? It's a page, and, D is the 0th bit of the page offset. The E, you probably start from that side. The E is it's 5 bits where it's all zeros and a 1 is the E. You guys get that? Right? 5, all the zeros and then 1 0 or 2 in binary might be the A. Okay, so you got that on that? All right, so people are nodding their heads. You have 4 physical pages. I've shown you a little example here where you have, here's the page number here, and you got the content. Dear Diary, yesterday, oh my God, did you? And then 61C is great. You got to put that in there because you love 61C. Okay? Questions about the model, the spec? Not too bad so far, right? Okay. What if I give you, with the nice little animation, what if I give you, they didn't have Wi-Fi back then, but let's say you go back in time and you give them Wi-Fi. What if you had a wireless connection to a disk? To a real hard drive. And that hard drive, remember the hard drives are small back then too. So all that hard drive had enough room for was 8 pages. Okay? So not a lot of storage we're talking about here. But let's just say it did. 8 pages. Okay? So I have 4 that can only live on my device because RAM is really expensive. Okay? What could you do? What illusion or abstraction could you give? Remember, we're Amazon, 1970. Jeff Bezos, I don't know how old he was. He was 7 or something like that, right? He's going to make his version of the Amazon Kindle. What illusion or abstraction could you present to the user if you had a connection to a disk that holds 8 of them? Yeah, and I want everyone's hand up. I want everyone to get this. Yes, no, that right there. Emily, yeah. You, Emily, right? Okay, Emily. Wait. That's true. But harder. Go smaller by 4. Yeah. Okay. Emily's going to say this. This is for the webcast people, so let me go here. This is important. That's exactly right. I want everybody to know this, everybody to love this. So go.
You can make it seem like you have 8 pages.
You make it seem like you have 8 pages. Huh? That's the idea of virtual memory. That's it. If you get that idea that even though you only have 4 physical pages on my device, you can make it seem like you have 8. Questions? Let's pause now. Anybody not get that idea? That's all. That is the only idea I'm teaching you today. So let's really pause and rest and reflect on the fact that you could give an abstraction to a user that they have all the space that you have to give them. 8 pages here, or, I don't know, maybe 4 gigs of a 32-bit address space. You see where we're going to sneaky? You sneaky, the connection? But in fact, in physical memory, you don't have that. You have a much smaller amount. What do we need to build that? What do we need to make this happen? If you understand how we're going to take our 4-page physical device and make it seem to the user that they're actually writing into an 8-page diary, you've got the entire idea of virtual memory right there. That's it. That's the analogy I'm trying to present to you. And you're going to like it. You're going to appreciate the fact that we're swapping in and out pages, and that's the exact name we use when we talk about the computer side. It's going to be really cool. And guess what? Reading and writing words. See, load and store words. See how clever the analogy. Okay, enough patting yourself on the back for your analogy, Dan. All right. So, it did weird things with my slides. This was not all flugity like that. This was, let me show you how, I blame society. So, this was a pretty thing that was supposed to go like that. There it is. Okay, that was weird, and that did weird thing. Okay. So, we'll distinguish from the physical this is annoying. This is I blame Microsoft for this one. Okay, so society is Redmond's society is what I blame. Okay, and this I'll just move over. Sorry about this. There. Okay, and we're back. You didn't see that. Okay, so here we go. We'll distinguish the physical memory, which are the things, the pages resident in the device, right? Here's the physical memory. That stuff that's resident in the device. Resident means lives there, right? In the device, with my virtual memory, which lives away. Virtually lives away, whether I store it on disk or a network, just lives away. Okay, you don't need to worry about that. Okay? So I have 4 pages physical. I might have 8 pages here. But you're going to notice journals don't start full. It's a journal because you start filling it up. You don't start full, right? Just like you write a program. You don't start using all 32 bits of RAM, 4 gigabytes of RAM. You don't have that. You have a little code, some static. Maybe it'll heap if you have some early Mallocs. Stack hasn't really grown, have main up there. So you don't use all the space. You start a journal with it full. You start it blank. You start filling it up. Virtual memory is bigger than physical memory. Okay. What's needed to keep track of which page is in memory and where? Look at this. Okay. Oh my God. Look at that. Where's my thing? Oh, the scrolling. I had this pretty animation. Okay. Again, I blame Microsoft for this. But anyway, the point is, Occupy Cal, which is here, is in the first slot. One day is in, actually, Dear Diary is in the, this is so bad. This is just, it worked perfectly, and then I changed the version, and we do this, and that's going to be very pretty. Okay. So, okay. Occupy Cal, one day, look, this is the whole thing. So, I don't want to play with it. But I had this nice animation where they're in different orders. Okay. That was so good, too. So you see how one day is here. But no, look, notice the, oh my God, did you? That kind of phrasing is so last week. So you haven't touched that page recently. So it's not loaded in resident. The ones you're editing are the ones you care about, right? So those are the 4 you want to have resident, the ones you're editing. And look, there's reordering of it. Because maybe this is smart and it has the flexibility to put it anywhere. And that's kind of cool. So that might be useful to you, where you like the first thing that comes up on the first page is from somewhere else. So that flexibility is really cool. Okay, so maybe this one. Does this one work? That one doesn't work either. This whole thing. Let's look at, I spend so much time. Okay, everyone note that the PowerPoint table problem has bugs. This is the PowerPoint table, and this was like, why is it doing the wrong thing? This is actually important to the learning process too. I'm going to give up. It's really, yeah, it's bad. It's bad. Let's look. So Occupy Cal is the 0 slot. Occupy Cal was number 6. So look, under number 6, I have to know that number 6 lives in the 0 spot. You see that part? And I'm going to have another bit that's going to tell me, is my virtual page, okay, is my virtual page, this is index of virtual page number, is that in the physical device or not? Okay, let's look. So what 4 is? Occupy Cal is yesterday, so 6 is Occupy Cal, that is, it's true, it is resident, and 0 is where it really lives, right? We got that first one. And the same for everybody else. Yesterday is 2, therefore 2 is resident, true, and it lives in 1, and that's in the first slot. 6.c is great, is 7, so 7 lives in the second slot, and day is, I guess that was probably yesterday. Yesterday is true. You got that? Do you get this table? Let's start right now, because we're going to pause to have questions about this table now. This is called the page table, right? You're keeping track of what pages are on your eJournal. So you need to know for all the virtual pages, which one of them are in the eJournal and where do they live. How hard is that? How would you store this page table? What does it look like? Like an array. This is an array. The index is this number, and what's in that is the frame number and whether it's valid or not. Right? So I have 8 virtual pages, therefore I have an array of 8 elements. Each of those 8 elements, I need a bit to tell me, do you live in the physical page or not? Do you live in my journal or not? If you do, I say true, otherwise false. If it is true, then I look at the next field which says, where do you live? And that's how I'd get to it. Okay? We so far on this? Okay, questions, let's pause. That's the whole thing. That's the whole idea. The whole idea is you got a virtual set of pages. The physical set of pages might be smaller, probably smaller, than the virtual set. You need to keep track of for every virtual page where it lives in the physical guy and whether it's there or not. Yes, question? What goes in the blank slots? The valid would be false. And I don't care about these guys. I should probably have put false there. Okay, that's a very good question and a poor PowerPoint table editing by Dan. Okay, so everyone actually, this is good. You have slides. Hey, everybody write in false in this column. Because there's a whole style of teaching where I leave stuff blank and you have to fill it in. That was intentional. Yes, that was intentional by me. Yes, I made that up just now. Christian.
Where would this array be stored?
I love it. I love it. Where do you store this array? This is an eJournal. It's got to be stored somewhere. So we're going to have to actually borrow some space in the number of pages and store it there. We're going to see that. That's good. That's a great point. But you're going to have to store it somewhere, right? It's stored in memory. Yes? Question? Good. Why do you have an extra column? Why do you have a frame number? This frame number is just bits. It's just pure bits. So how do you interpret those bits are real bits or not? You want those bits to be every possible space for those bits to be real. Meaning, what I'm saying is, how many different, let's talk for a second. Great point. The question is, why do I need this valid column, right? Why can't I use this guy? How many bits would I use for frame number? Look at this. It's number 0 through 3. How many bits is that? 2. So therefore, I'm only going to store 2 bits in my frame number. So there's some numbers in here. There's 2 bits in all these values. Are they real or not? I don't want to reserve, a sentinel page to not be useful. I want to use all of my probable bits, so I kind of add 1 extra bit over here to tell me whether I should look at that or not. That's a great question. Or has one.
So you were saying that the page table is going to reside on the eJournal. Why is it not also on the whatever virtual memory system?
Why doesn't the page table live on disk? You want to keep it resident. It's important to have it resident there. We'll see why when we get to the real system. But it keeps resident on the system. Trust me on that one. Okay, good question, though. Keep going.
Why did you limit yourself to 8 unique pages? Why not 12 pages?
This is great. Going back to Emily's initial question, why not go with 12 pages? Well, let's say you went to 12. What would you do with 12 pages? You have no more memory. You've used up every bit you have. And now you want to borrow and swap. How do you swap if you have no place to swap? So you don't want to have 12. But how about 11? You can actually go with 11. But it makes it more complicated. So there's something about, you're right, you could stretch it a little bit more, and you're exactly right. But for this case, we're going to stay with 8 just to be clean. Does that make sense? You'll see why when we get to bigger things. Okay? Yes, question. Christine in the front. I love it! Christine, it's a great question. Best question so far all day. Thank you. You said disk. Remember disk? You know how far? Remember what was disk? How far was disk in our Drive to Sacramento model? Like Jupiter, right, or something? Right? Mars? That's right. It is on disk. It is crazy. So what does that tell you about which 4 pages you want to make resident? Say, go loud, go. The ones you want to use the most. The ones you're using the most frequently. Exactly. Temporal or spatial locality we're talking about? Temporal, right? Excellent, okay? So you might want to make sure you never go to disk. You want to optimize for that. And in fact, I'll even let you have extra data structures to make sure you're really smart about which pages you kick out and which pages you keep resident, so you never have to go to disk as much as possible. Be smart about that and do everything you want to do as much as possible. Exactly right. Okay, so I'm going to show you a simulation of our eJournal. It's going to look like a complicated virtual memory thing, but in fact, this is my eJournal. Yes, Rohan.
So does that mean that the memory that we have, the physical memory that's not on disk, is that just like a cache for the disk?
Ah, you, my friend, are a plant. You're going to postpone that question for exactly one slide. Say, you're going to raise your hand again at the end of the next slide, and then you're going to ask the question again. Trust me, okay? So nobody heard that because it's going to be a great lead-in. Okay, this, my friend, might look like a complicated virtual memory thing. This is our eJournal. Here is physical memory, and there are 32 spots. For page 0, 32 spots, 32 characters for page 1, 32 for page 2, 32 for page 3. This is all the physical memory I have. Here is my virtual memory. I have 8 pages. See how clever the connection, 8 pages to 4? You're going to ignore this. Everyone, look, shield your eyes from this thing. You're shielding, you're going blind, you can't see it. Put the thumb up. Everybody see the thumb. Block it. I don't want to see anybody look in this ear. If I see an eyeball looking up there, you're doing the wrong thing. Excellent. Keep the thumb up. This is my page table. Like we just talked about. Remember the page table that keeps track of whether it's valid and where it is? And watch this. I'm going to say auto-generate requests. These are requests from the user for a particular character to read or write. Okay? So, what did I say before? I said we have 8 pages, and each page is 32 bytes. Okay? That's 5 bits. How many bits is 8 pages? 8 things is 3 bits. 3 bits plus 5 bits is how many bits? 8 bits. Those memory addresses are how wide? Each hex digit is a nibble. That's 4. 4 plus 4 is 8. There's my 8 bits. That's accessing a word on your eJournal. Okay? So watch how cool this is. This is a great simulator. Next. It says 9F. Okay? 9F. Ready? Let's do it. By the way, if this goes slow when I spend the whole lecture in here, that's actually okay. So don't worry about the fact we have to get slides to get through. I really only have 2 days of slides and 1 day of demo. So this can stretch into a 3-day thing. So 9F. The user said, I want to touch and update or read 9F. So watch this. Virtual address bits. I love the Mac. Zoom. Now, 9F. So when you map 9F into the bits, 1001 is the 9, and there's my F. Okay? The lowest bits have always been in caches. What was it? Tag, index, offset. What was the lowest bits always? Offset. The thing inside the page. So that is what guy inside the page. Which one is it? Which character is inside the page? The last one. All ones. It's the 31st guy in that 0 to 31. Number 32, it's index 30 to 31. Page is 100. That is the virtual page. Of the 8, that's a number from 0 to 8. 3 bits, right? So what does that say? 4. So I want virtual page 4. Watch this. Next. So I go to my page table. I say, where does page 4 live? Does it live in memory? Nope. Because it's not valid. And this frame number is, remember, like garbage, right? That's why I put the valid bit, because that can be garbage. So now I hit next, and I say, okay, zoom back. And now, it's going to be page 0. Put in the first page of my ebook, right? My first page of my ebook has my thing, okay? And watch this, keep going. Virtual memory page 4, I just showed you that, right? Okay. And now, again, you're ignoring this part up here, right? Okay, page, I'm going to put into 0. I'm putting in a physical page 0, so my table, which is just an array, we agree with that, my page table shows in row 4, row index number 4, the valid bit is 1, because it does live resident. Virtual, this is the virtual page. Physical page 0, and this is physical page 0. And look at this, here's the cool part. I look up here, this is the frame number, which is the page, the physical page number, and that is fewer bits than the virtual space, right? I have 8 virtual things, but only 4 physical things. So the number of bits I use for my physical thing is fewer bits. Therefore, that's an entirely different number. That's 0, 0. See, I went from 4 to a 0, and that's what this is. Under 4, I look up 0. And I access, look at this black guy. It's the last character of that physical page. Okay? Look at this. And next. This completes an access cycle. Let's pause now, because this thing lets me back up. Bank, 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 bank. Okay? Questions about that access? You just successfully watched an e-journal simulation. If you got that, if you actually, honestly, followed every step of that, you understand virtual memory. That entire thing was virtual memory. That's it. You have this table in the middle that keeps track of where you are, indexed by the virtual page number. Indexed by the virtual page number. Notice this isn't indexed by bits 8 zeros to 8 ones. It's only indexed by the leftmost bits of the page number. Right? Because you're talking about what page you want. You want about, oh, I want the 4th page on my journal. So you're not accessing by all bits, only the numbers 0 through 8, which is only the 3 bits on the left side, which is the virtual page number, the VPN. Okay? All these things don't make sense. If you go back to the e-journal, always, that model will work for you. Keep the e-journal in mind as we're getting complicated, we're doing other things. It's all about the journal. You got 8 real pages in your journal, 4 that live in your device. Question in the back. Go. Yes, you're left. The user, okay, so I guess there's the user is thinking, what is the user thinking? In physical space or in virtual space? Right, the user should be thinking in virtual space. The user says, I got 8 pages. So I want to go to the 4th page, so it goes flip, 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 kind of virtual, 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 and it says I want to access, and what the access was 9F. So the user's thinking in virtual space, always. Now tell me your question, again. That's a question about the UI and let's just say there's a Kindle that says, what page do you want to edit? And you type in a number, and it's a number 0 through 8, and it says, okay, now start editing it. You say, okay, it'll say you're now editing page 4. And it's going to show up as the first page in its physical device, but there'll be an interfacey thing where it says what page do you want to be working with, right? That would make sense. Good question to ask. Yes, there's a follow-up question here on the left. Yes, go. Same question, okay. In the back, yes. Uh-huh. Excellent. That's exactly right. So the question was, so the question was, okay, once we found that it wasn't resident, I got to find a place to put it. So really, there's got to be a kind of another table that says, is there any room in my physical device? That's correct. That's exactly right. You made a read or write access, and so what it's going to say was you're probably going to be using that again. If you make a write, you're probably going to be reading it soon anyway. So it says you made an access to 9F, which means page 4. I want to put that in resident, so if you start reading and writing anything, it's ready to go. Now, the question of where did I go in my physical device is a good one.
You have to decide which one.
Exactly. I happen to have 4 open, so I was totally fine. What's going to get interesting is, what if I have 4 that are full? Yes, but there's nothing on this page. Right. Your answer was get rid of the one you want to use the least often, the farthest back in time. But there's nothing here that keeps track of that ordering. So that has to be added as part of the to make this really work, you got to have that. So, and then you update this whole list of, it's like a Windows. When you click on a window on your physical device in a WIMP operating system, you have the ranked order of all the windows you have. Same kind of thing. Yes, question here. Good. Does physical memory start blank or garbage? What do you guys think? Garbage.
So if it starts garbage, let's say I first added like page 1 on virtual memory.
Uh-huh.
Then I added 4 other pages that aren't page 1, and then I ask for page 1 again.
Right.
Then how does it, what does it show? Does it show to me like a bunch of garbage and then?
It never shows you garbage. So maybe your question is, if I go through and I access, like, let's say 4 pages, and then I access a 5th page, what happens? And that's a question. I hope in this random string we end up seeing that. So there's a 5th page situation. But the reality is, as you'd guess, what would you think? Let's talk through an algorithm. What would happen if you now access the 5th page? We say you got to look up who the oldest one is. So what do you then do? Take the oldest one, put it back to disk. You might have made changes locally because you're a journal, right? You're reading and writing. You never want to have to go to Jupiter, but you got to. You go take this and make the long walk to Jupiter and take the oldest guy and put it back. That page back, right? You wrote, oh my God, that's the oldest one, right? You put that one back because you never want to go to disk ever. You keep it. The most recent copy is always physical memory because you never want to go to disk. So there's inconsistencies about what the page had back there and what the page was in memory, right? If you loaded the page with data and you made changes, you never want to go to disk. So you always keep the most recent copy in physical memory. What that means is power goes out, you have lost state. The stuff that was there, if you never want to go to disk, so unless it got kicked back out, it's not been stored. If the power goes out in the middle of something, and that can be how you lose data, honestly. But once that old page, that old dry stank page you haven't touched for a while, that has to go back to disk. You pick it up. You write it, okay, long walk to disk, write it. Now you're Jupiter. And while you're there, you might as well be loading the one you wanted, right? The new 5th page. And you go get that, and you put that in whatever the spot that the old one was, and then you're ready to go again. Exactly right. So there's no details here, but that's exactly the algorithm that I hope kind of emerged like a good Occupy movement did, and you did. That's perfect. Good job.
So when you're opening that 5th page, is there a lag with that, or does it happen like parallel or something like are you swapping out the
If you're opening that 5th page, that's a long time to go to Jupiter. So in a real computer system, that might be a chance to give somebody else a turn to use the CPU. That makes sense, right? So all of a sudden, not there, right? Now here's the cool thing. I wanted to use this kind of phrase. I didn't have it on a slide, but let's talk about this. One of the things that I've noticed in your generation, and less so of my generation, but your generation, is the inability to take responsibility for something that's your problem. It's society's problem. I remember, watch me, I blame society for my PowerPoint ineffectiveness before, right? So, I'm going to actually, and the only time I'm going to suggest that you do that in this class, for this exact moment. If you have to go to disk, right? If you have to mess up and go to disk, and I was looking for page 5, it wasn't there. Whose fault? Is it your fault or is the page's fault? It's the page's fault. So from now on, I want you to think, it's not your fault, it's the page's fault. And guess what? You know what we call it when you'd have to do that? A page fault. And that's it. Wah, wah, wah. Okay? So, we're having fun today. All right. So, page fault when you get to a case where the guy's not there. Any other questions about this so far? Yes. Christian again. There's write through and write back. We certainly want write back. You never want to do write through. Write through says, you make a store word, goes to disk. You've got to be kidding me. So it's definitely write back in that sense, which means you have a dirty page. Ooh, very important. Christian brings up a good point. Do I have to write the old stank one back or not? Well, if it's write back, you remember we have to have another bit that tells me whether this thing has to be written back or not. If I've made no writes to this page, then I don't have to write it back because it's consistent with the guy that's on disk. So I don't have to do that. So therefore, you see that there's going to be another bit called a dirty bit that'll keep track of whether that page has to be written back to the disk or not, which is another trip to Jupiter that you don't want to make. Okay? Good point. Yes, right in front.
You have a table that has correspondence between virtual memory and the 4 physical pages, but you also need to have one that has like the correspondence between virtual memory and where it is on the disk, right?
Yes. The OS is going to take care of that for us. So where it actually lives on disk, not our problem. Essentially, once a page fault happens, we say page fault, then the OS takes over and says, don't worry about it. It's very much like I go, like the abstraction as if I had a butler with me. And I go to my fridge and there's no orange juice. So I say to my butler, I want some orange juice. And I walk in slow motion. The butler knows there's no orange juice there, right? So rather than as soon as the page fault would have happened, the butler goes and gets orange juice without me knowing it. What's that movie that you slow motion, you kind of freeze? Like there was a Adam Sandler with like a push the pause button, fast forward or something. So I go, orange juice, and I freeze, and I don't even know. All of a sudden, the butler goes, buys the orange juice, puts it in there, and by the time I go, it's there. You see how that's the abstraction we want to keep. From the point of view of a load or store word, you don't need to worry about when you have page faults and it's not there. It'll always be there. This virtual memory system is below your level of abstraction, so you as the programmer, either C or MIPS, never need to worry about a page fault. It's always there. This is just an ability, an abstraction that makes you think that physical memory is infinite. I mean, 32 bits wide. Yes?
You said the page table is stored as an array, right?
Yes, page table is an array.
It's indexed by virtual page number.
Indexed by virtual page number, exactly right.
So if we index by page number, the array becomes half of it, and we don't need column in.
You want to reverse the table somehow. Well, I need to know whether it's there or not. So I still have to have this. Now, you're saying, is there use to having the reverse mapping?
What I'm saying is that we can have a table 0, 1, 2, 3.
Yeah. So you're saying over here, I put a little label that says where I am and who lives there. And every time I make a request, I have to then go check every one of them. That could be annoying.
No, like 0, 1, 2, 3, and just the virtual page address.
No, I got that. But you're saying if I access virtual page number blah, if I only have your array, I have to then search through every single element in my physical to say, is it there? No. Is it there? No. Is it there? No. Is it there? I don't want to do that. It makes more sense to have an immediate access. It's a lookup. It's a lookup into array. I don't want to have a search. It doesn't make any sense. You do array. You do memory I/O fast enough that you want to be able to sweep through all the pages in your physical memory. That's crazy. Okay, so let's do some more. 3D. Let's see if we can get funny. Ooh, I like 3D. I'm a graphics guy. I like 3D. Here we go. Okay, 3D. There's my virtual address bits split nicely into my virtual page number on the left and my offset on the right. Okay? So now I say 1. I go over here to 1. Up to index virtual page number 1. Invalid. So therefore, it's not there. So that was... and by the way, you can read this, and it says it here. Look, since the memory has empty space, the first available frame will be filled. Highlighted as the memory frame into which the page will be brought. Just exactly as it's so cool. So this is a really useful thing that you'll actually see yourself. So I'm accessing page 1, and I fill this stuff in. It's the same as 9F. That's exactly the same. Okay, next one. A4. Oh, look, another page. Now that's virtual address 5. Ooh, that's the third guy. Bink, there, and now there. See, it's all making sense so far? Nothing new. Ready? Next one. AF up. Oh, look at this. Look at this is. By the way, each of those first 3 were page faults because they weren't in physical memory, right? Whenever they're not there, I have to go to the disk. In theory, they were all lived on disk first. So now, page 3. But watch this one. Page hits. I had no page hits. I had no time where I accessed something that was resident. But look at this. Virtual page number 5. Page number 5 is resident. Yeah, and look, it says here, see, P5, P5, P5. This is like page 5's offset. That's a little index there. So watch. I hit next, and watch, it says, ignore this, okay? And then, what does it say? As we set it up, Okay, page 5, and page 5. Where's my update page hit? There's no page hit. That should have been 1 now. Yeah, well, it's because that's annoying. That should have been 1. It was a page hit. I had it there. Okay. So let's keep going. 9 is a 4. I already have 4. That's not interesting. Okay. 7. I like 7. 7 is a 3. I like that. Oh, now I'm full. Now I have 4 pages all full into my e-journal. Okay. Now let's do the next one. This is so cool. Oh, I think this is going to work. Yes, this is going to work. Woohoo! Okay, let's slow down now. I have accessed address 13. 13 maps to, is that 13? Yeah, 13. Okay? That has accessed virtual page number 0. So go slowly. Like in the old days we had the $6 Million Man. Okay, only Mike gets that reference. Okay, not even that one. All right, what back? Okay. So, that used to kill in 1974. So, page table, virtual page number 0. We go over here. Is it valid? No, it's not. Then some other data structure, I keep track of this. I say, oh, full. What do we do? Who do we kick out? Again, not in this. There's nothing on this screen that shows you who the oldest one is. We know the oldest one is the first one, right? So watch that. Here we go. Next. Okay. Memory is full. The least recently used memory frame will be replaced. Highlighted is the victim. Ooh, I like that. The victim memory frame which will be replaced. So now we ask ourselves, what's the dirty bit on that page? Remember, Christian, is it dirty or not? I don't know whether it's not clear whether this is a read or a write up here on the right guide. This is just address reference. But in general, it's either a store word or a load word, right? If there were no store words to that page, it's not dirty. And I can just kick it out for free for no cost. Okay, I can just clobber it. I don't do anything. I just basically override it, and it just overrides it. If it was dirty, I have to write the whole page back. Okay? So, here we go. That's the guy that's out. And now, watch this, page 0. And now, blink, page 0. And now I hope this wasn't lost on you. I then look to my offset, and I count in, this is 13, I guess. No, that's 13. This is the number, what is that? Looks like 19. That's 19, right? So, I again find byte 19, and that's the byte that I access. Okay? Pretty good. That was it. That's enough. Everything else I'm going to do is just going to be repeats of that one. That was the first one that was interesting for a long time. Okay? Questions about that? Was that helpful at all? Christian, last question.
Would you ever want to look at the dirty bits and then kick out something that hasn't been written to because it'd be faster than like making a write and then?
Ah, very clever. That's very clever. That's a good question. Rather than thinking about LRU, maybe you think about the guys that aren't dirty, and that would be a cheaper one. But here's the problem. If you do that, what if the guy who's just been reading all the time, every single time, he's not dirty? He's the only one not dirty, but he's the guy you've been reading to every single... Certainly that's the last guy you want to kick out, right? So you still want to kind of preserve the LRU model of that in terms of replacement. Okay? All right, well, that was a simulation. This is what we're doing. This is the big picture. And now we're back to normal 61C slides and description. But that entire day spent going really slowly means that all this stuff you've seen, hopefully all this stuff like, oh, I get it now. It's the same idea. So here is the memory hierarchy. We see how valuable that is to think about in the space of computer engineering. Registers, cache, L2, maybe an L3 in there. I have memory. Blocks have been the unit of transfer back and forth. And blocks are small, right? Blocks are some number of bytes. But when pages, if you're going to disk, if you're going to Jupiter, you better give me a lot of stuff when you're there. Partly it's because it takes a disk physically long time to seek to the right place, but once it's there, it can actually stream data pretty fast. So once you're there, giving me a lot of stuff is actually not painful. So you give me a lot. So page is going to be much bigger, right? On the orders of kilobytes, not just bytes. So pages is this, and disk is really another layer before tape, and we use files to think about that space. But pages is what we're doing today, and before you've seen that, and now you're learning this stuff. Virtual memory is everything here. And the benefit is, and this is all things I've said. In a way, this is all things I've said, right? Which was, if the principle of locality allows caches to offer things at the speed of a cache, but at the size of memory, why can't we do the same thing with memory to disk? At the speed of memory, but the size of disk. And what that means is disk is typically bigger than 4 GB, so therefore I can virtually give you all of 32 bits address space even though you don't have it. Even though you didn't have it certainly back in 1970. But you could have been writing 32-bit wide programs that did a Malloc on roughly 32 bits of data. You could have a Malloc of 3.9 GB in 1970. And as long as you had 4 GB of disk space, it would say Malloc will return a non-zero number. Isn't that cool? Malloc wouldn't fail. That's really cool, by the way. And that's how all along, thanks to this, all along, for the last 20, 30 years, you've been able to think, oh, that's right, you have all 32 bits of address space to access, even though no one. Raise your hand if you have more than 4 GB of physical RAM. 3 of us, 10 of us. Are all of you writing 32 bits programs and doing big Mallocs? Yes. How does it work? Because you got disk. Because you got disk. Okay? Now, I happen to have 8 and 16, but still, it's okay. All right. So, here's the other cool thing. What you haven't seen is, yes, that's nice for your journal, but how about this crazy idea? How about if you have a big enough disk in the back room, you can actually have multiple people in your family have 8-page journals on this e-journal. Does that kind of make sense? You can have multiple users sharing the same physical RAM, and yet it just seamlessly feels like I own the whole thing. When I go into my journal, I start to read and write. Now, maybe there's a way that when I load it in and log in, it kind of cues away my sister's journal, so I can't read the special things she's had and all the things my mom has had. But it might load up for me in the journal model. But in the program space, you don't actually access the physical RAM. You only access virtual stuff, so you never actually see. That's why this model, this analogy doesn't fully match, because you're actually seeing the physical side of it. But in the programming side, you only see your virtual side, so that's okay. You can have multiple users share the physical thing, but you're never actually touching the physical thing, so it's okay. But that's why the e-journal model kind of breaks down, because like, oh, wow, look, mom's journal. You're not supposed to see that kind of thing. Okay, the other cool thing is, so you have protection. So I have my virtual address space. Because I'm not operating on the physical thing in the virtual space, I can now have two people sharing the same physical space, and I have protection. Each process thinks it has all the memory to itself, and this is actually before caches. Caches was an optimization used because the CPU memory distance got too big. But we've needed to have 32 bits of address space, and back in the day, 16 bits of address space for a long time. So this actually exists before caches, which is actually really cool. And remember, I have a working set of pages. See how the analogy is still the same? Resident and main memory, the same as you guys have understood with today's lecture. And look, you know this mapping now. The program operates in virtual address space. You have a hardware mapping. You have a virtual address, which converts to a physical address through that table. That page table tells you the physical address. It's so brilliant. Okay? So cool. The OS decides where things go, and this hardware mapping tells you where things go. So here's a picture, and I'll probably stop on this slide. So I divide the world into equal-sized chunks. And the awesome thing about doing that, and the same reason why if you look in Walgreens or CVS in the toothpaste aisle, all of the toothpaste just fits perfectly because it's all a rectangle. And it just fits perfectly into there's no gaps ever. I mean, maybe they run out of stock or something, but there's no gaps. There's no fragmentation. Remember memory fragmentation where there's like a little sliver there? What if they're all the same size? You don't have fragmentation because it's all full. Watch. They're all the same size like toothpaste. There's toothpaste. There's a little toothpaste box. And guess what? They just happen to map, as I showed you in my very faulty PowerPoint thing. This is a much prettier one, how they map. And you don't need to worry about that. You don't need to worry about this table. You think in this space, I've got some stack down here going down, a little recursive guy. I got some Malloc action. Here's some static stuff here, and here's my code. That's how you think. You don't use all of it. And the reason that I benefit, the rest of the users benefit, is that because you don't use all of it, now I can actually have many full programs fully resident. Because your journal, you had like 2 pages. Let's say you don't like to write that much. You don't need all 8 pages, so I use 2 of them, and they live resident. They're always there. It's only when you have memory hog people, like a renderer or a Photoshop or something that needs every page, then you have trouble. Or, some MATLAB array or something like that. Okay? I think I'll stop with that slide. That's the key. I hope this is helpful, folks. If you got the journal model, you get the whole idea. We'll start right into this with the same set of slides next time. Thanks, guys.